So let us look at properties of dielectrics. What are the properties of the dielectrics that we are interested in, and which decides whether a material is a good dielectric or not? The first property that I'm going to look at is DC conductivity. This may seem a little anomalous because we have just now said that dielectrics are materials which do not allow conduction of current. But that is true for an ideal dielectric. An ideal dielectric would have zero conductivity, but a practical dielectric would always have a finite value of conductivity, and this finite value of conductivity sigma is given by the ratio between J and E, where J is the current density resulting from the application of direct electric stress E. So you have a dielectric, you apply a direct electric stress E across the dielectric material, a current will flow through the inside of the material, and the current density is given by J. So DC conductivity is nothing but the current which flows in the material, whether it's a conductor or a dielectric, and which is governed by Ohm's law, which is V equal to IR. Sigma is J is equal to sigma E is nothing but the field theory representation of Ohm's law. The sigma is a property of the material, and you can measure it, you can obtain it once you are able to measure the value of the insulation resistance of a dielectric material. We will discuss that later. But apart from that, there are certain other factors which govern the conductivity of a material. For example, material purity. If you have a lot of impurities in the material, it means that the conductivity will be higher. And it also depends on temperature and electric stress. The manner in which sigma depends on temperature and E is given by this relationship. Sigma is equal to e to the power minus E by kT, where E is the electric stress that is applied across the material, T is the temperature, absolute temperature in Kelvin, K is Boltzmann constant, A is a constant. Why are we interested in the DC conductivity of a material? Whenever you have a current flowing through a material, you would also have I square R losses. I square R losses means there would be power loss from the system. So therefore, the DC conductivity of a material decides the power loss that you would have from the dielectric. Apart from that, it also controls the electric stress distribution. So when you apply a direct voltage across the material, what would be the nature of the electric stress distribution within the material is also governed by DC conductivity. Now, electric fields we will discuss later. The second property is the dielectric constant. This is, however, different from dielectric permittivity. The dielectric constant, I can define that as the ratio between two capacitances C and C naught. What are C, what are C naught? Let us take an ideal parallel plate capacitor. So I have two parallel plates which are separated by a distance, and I place this particular material between the plates, and I measure the capacitance. Let us say this capacitance is C. Now I remove the material and replace it with vacuum. So you have the same parallel plates, the same gap distance, and they are now separated by vacuum instead of the material. So let's say the capacitance is C naught. The ratio between C and C naught is given by epsilon R. Epsilon R is, of course, a material property and therefore dependent on the molecular structure of the insulating material. It is also dependent on temperature and frequency, and that is something that we will discuss later when we discuss polarization. Now, the reason I say that we are not going to consider epsilon R as the permittivity as we often do, but we are separately going to call it the dielectric constant, is because permittivity is actually a complex quantity. It has a real part, it has an imaginary part. So your complex permittivity of a system is given by epsilon equal to epsilon dashed minus J epsilon double dashed. Epsilon dashed is the real part of the permittivity, and that is nothing but epsilon R, or the dielectric constant that we discussed in the previous slide. Apart from that, we have the imaginary component epsilon double dashed, and epsilon double dashed is related to the real component by this quantity epsilon R tan delta. Now, so epsilon R is the real part, it is the dielectric constant, it measures the ability of the material to store electrostatic energy. And the imaginary part gives us a measure of the losses in the system. It is related to the real dielectric constant by the term tan delta. The tan delta is the loss tangent or the We also call that the ton delta quantity. And the imaginary component gives us a measure of the losses in the system. So let us take a look at loss factor, because we are often concerned with measuring the loss factor of an insulation system. If you have a material, a dielectric material, and you apply a direct voltage across it, across the material, there will be two currents flowing in the material. There will be a current IR, which is in phase with V, and that is given by the DC conductivity. IR is equal to V by R. And there will be a capacitive current, which is 90-degree out of phase, which is given by J omega CV. So that is dependent on the frequency and the capacitance of the system. IC and IR taken together gives you the total current in the material, which leads the applied voltage by an angle theta. Delta is the angle between IC and the resultant current I, and tan delta is called the dielectric dissipation factor or the loss factor or tan delta. It is the ratio between the two components of current IR and IC and is equal to 1 by omega CR. It is also the ratio between the imaginary and the real components of the complex permittivity. The most important property is, of course, the dielectric strength. When you apply an external electric field across a dielectric material, it does not allow current to flow through. But that is only up to a certain point. If you keep on increasing the electric stress across the material, and remember, I'm not talking about voltage, but I'm talking about electric strength or electric stress. If you keep on increasing the electric strength, then there comes a point at which the dielectric loses its dielectric property. It becomes conducting, it is shorted, it fails, it is punctured, and it loses its dielectric property. It becomes conducting in nature. So this minimum fill, the maximum fill that you can apply across a material before it loses its dielectric property is called the dielectric strength of the material. And when you cross the dielectric strength of the material, if you apply a field greater than the dielectric strength of the dielectric material breaks down, undergoes electrical breakdown. The dielectric strength, of course, depends on the material. For gases, it's lower. For air, it is 3 to 10 to the power 6 volts per meter. For porcelain or mica, much higher. Like for mica, it is 10 to the power 8 volts per meter. So for a dielectric to be used in insulation, you have to be able to operate it below its dielectric strength. Though I have already talked about conductivity, there is one more point that I want to make about resistivity or conductivity. It is the same thing. Now, in talking about dielectrics, we talk about two different kinds of resistivity. One is the volume resistivity or conductivity, and the surface resistivity. The reason is that when we are talking about a conducting material, when you apply potential difference across 2 points, most of the current will flow through the inside of the material, through the volume of the material. But in case of a dielectric, there will be considerable, if you apply potential across two opposite edges, there will be a lot of current flowing through inside of the material, and there will also be some current which is flowing along the surface. Now, the volume resistivity is what determines how much current will be flowing through the inside of the volume of the material. It is defined as a resistance between two opposite faces of 1 meter cube of insulation. So you have this face, and the resistance between the volume, between the two faces through the volume of the dielectric is called the volume resistivity. Apart from that, you have what is called surface resistivity, which is the resistance between two opposite edges. This is one edge, this is another edge. The resistance between these two opposite edges of a unit square material along the surface of the material is called the surface resistivity. This is important for assessing the state of surfaces when you use it either in air or in gas systems. And we have to be concerned with both the volume resistivity and the surface resistivity of a dielectric material before you can use it in any insulating application.